Good morning, good afternoon, and good evening, and welcome to this talk on how the evolution of electric drives is changing copper corrosion testing. My name is Greg Hunt, and I'm from Lubrizol, and later we'll be joined by Greg Miiller from the Savant group. In this presentation, you'll hear about the challenges of corrosion testing and how we use these corrosion tests to ensure that corrosion doesn't become problematic for hybrid and electric vehicles. Tighter CO2 emission targets are driving OEMs to develop electrified vehicles and full electric vehicles. The choice of where to position an electric motor in these vehicles is varied, along with whether that is incorporated within the transmission. At present, conventional fluids are used across all vehicle platforms. However, bespoke fluids are enabling new electric motor designs. Copper corrosion could cause severe vehicle failure in an electrified transmission. And this is one area where conventional lubricant deficiencies due to hardware changes may exist. For example, the introduction of the motor winding in contact with the lubricant brings about a new operating condition. There's a much wider range of temperatures accessible to the lubricant. For instance, the bulk temperature may actually be lower in a hybridized vehicle than in a conventional one. However, the motor windings may experience significantly higher temperature spikes of up to 180 degrees Celsius. Furthermore, vapor phase corrosion is a key concern because these motor windings are either spray or drip lubricated. Traditional alloys or metals used in devices can now experience stray currents or indeed be powered as sensors, and this energized corrosion phenomena can bring about new corrosion concerns when interacting with the lubricant additives. Finally, the use of electronic control modules or circuit boards in these devices can bring about challenges on their own. In fact, one of the concerns here is with conducting layer deposits forming and causing a short circuit in the small spaces between the component chips, and we'll hear more about that in just a minute. Now let's have a look at an example of severe failure from a conducting layer deposit. In the first generation electric motor, the lubricant used was a conventional ATF and has excellent ASTM D130 copper corrosion strip performance with a rating of 1A. The strip can be seen on the left hand side of the screen now. Unfortunately, the time and temperature conditions used in this ASTM D130 strip rating do not correspond to good corrosion performance in the real operating condition of the electric motor. In this example, the ATF is able to come in contact with the copper in the motor as a result of the motor winding manufacturing process or a result of coating failure during operation. This results in the formation of a conducting layer deposit. As this deposit grows, if it comes in contact with other phases of the electric motor, it allows for current to flow via the deposit. This results in elevated temperature through the deposit, leading to further decomposition of the material and ultimately failure of the electric machine. So the question now becomes, can corrosion tests predict problematic corrosion issues? And let's revisit the ASTM D130. Looking at 3 lubricants tested for the same time and duration, you would select both lubricants 1 and 2 as good performers from this test, whilst you would discount lubricant 3 due to its 4B corrosion rating. However, this test is very dependent on the time and temperature that's selected and doesn't give you an insight into the corrosion rate on its own. For that, you need to use the wire corrosion test. If we look at the wire corrosion test, which can be used to also generate temperature profile maps, you can see you get more detailed information about the lubricant's behaviour. In this example, lubricant 1 has both solution and vapour corrosion rates almost negligible, whilst lubricant 2 has a significant amount of vapour phase corrosion. Lubricant 3 also has high levels of vapour phase and solution corrosion. Using this method, you would likely only select lubricant 1, whilst lubricant 2 may require further study. Whilst this test gives you information about the corrosion rate, it doesn't necessarily tell you about the corrosion product, and for that we need a third test. The final corrosion test here is the conducting layer deposit test. In this example, you can see that lubricant 1 is the only one that provides protection from corrosion deposits in both solution and vapor phases. Lubricant 2 does not provide protection in the vapor phase against conducting layer deposits, whilst lubricant 3 provides no protection against conducting layer deposits in either the solution or vapor phases.
Thank you, Dr. Hunt, for that stunning introduction. My name is Greg Miller, and I will be continuing on with the rest of the presentation, talking about the instrumentation that ensued from the work that was started by what Dr. Hunt was describing. My name is Greg Miller, and even though I don't have that really interesting accent that Dr. Hunt has, we'll try to keep it interesting nonetheless. So the test methods and equipment were agreed upon that not only are there areas of interest, but ones that really need to be pursued. Focused on corrosion deposits and conductive deposits, those concerns really were brought forth by a technical study team. That team gathered together and began to plan out how to resolve these issues for the industry. The study team formed comprised Ford, APL of Germany, Savant Group of Midland, Michigan, and Lubrizol. That collaborative team put together some recommendations to move forward with for the SAE TC3 AV task group. Two examples where research and development led to these areas, these EV studies, were some Lubrizol R&D, where the wire corrosion test and some conductive deposit studies ensued, and APL in Germany, where truly the conductive deposit test gained ground and grew. The goal of the team was to develop 2 commercially available tests for the industry. Today we will discuss those 2 tests, one being the conductive deposit test, the CDT, and the second being the wire corrosion test, WCT. Let's be a bit more specific. So there are 2 tests that were evaluated. One being a study of the conductive deposits that can be formed in an EV motor. Basically, a chemical reaction of the lubricating fluid that occurs, and the deposits that are formed become conductive and destructive. This test evaluates both in the vapor and fluid state. The second being a study of the corrosion and depletion of the copper and the wire, both again in the fluid and vapor state, both under voltage and in elevated temperatures. We will focus first on the conductive deposit test, also known as the CDT. As it turns out, the CDT is excellent in differentiating different drivetrain formulations and varying corrosion rates over time. Now, as mentioned, these are evaluated both in the solution and the vapor phase. The temperature of 150 degrees was selected. However, this instrument can ramp between 130 to 180 degrees C if desired, or other, to evaluate specific conditions depending on the drivetrain. For the purpose of this test, the studies were done at 150 degrees C. The circuit boards are electrified. The traces on the circuit board are then monitored over time, and as conductive deposits are formed, those become very evident in the graphs that you'll see in just a moment. CDT test setup. As noted here, one can see the critical spacing between the circuit boards that is provided by the assembly. In that proximity of that distance, the conductive deposits are formed, and also on the outside. Here, one can see the fluid level, which is here. So the fluid fills up to this level. Then this would be the vapor state, and this would be the liquid state. That is lowered into a bath at 150 degrees C. The voltage loops are both on the inside and on the perimeter in both phases for proper analysis. Once the fluid is placed into the chamber, the boards are put in with a cover. The test cells are then loaded into a carousel. That carousel will be put into either a dry block or liquid bath. Then a 5-volt DC signal is supplied through the duration of the test. The shorting due to deposits or an open due to failure of the copper runs via the voltage resistance tract over time. Testing can be up to 1,000 hours. However, we have shown that it can be reduced between 400 and 600 hours by some recent analyses. Okay, now we get interesting. We get to look at two fluids that failed in the industry. And they failed here, both in the fluid itself and in the vapor. We have two samples. Sample 1, as you see here in resistance in ohms, where we have max resistance at the beginning or high resistance at the beginning between traces. Those are between copper traces on the circuit boards. And as time goes on, you can see them reducing until finally the conductive deposits are conducting. The same happened in the vapor state with sample 1. Both are somewhere between 200 and 450, and then 100 to 300 hours here. Then sample 2 basically performs the same way, but further into the test. This one between 700 and 850 hours, and here between 600 and 750 hours. So let's take a look at a passing fluid. This particular one is a known good performing fluid, and here's what we expected. Turned out to be pretty good. So at the very beginning, you see the standard drop over time as temperature increases. The resistance does decrease as normal, but then it stabilizes, and it pretty much holds throughout the entirety and duration of the test, both in the fluid and in the vapor state. This particular fluid, no matter how many times we have run it, and no matter what laboratory, has always passed. When it comes to a visual analysis, it's really not difficult to distinguish between a passing board and a failing board. As one can see, as the copper is broken down on these traces and it begins to have the deposits build up and begins to arc, you can see why the resistance decreases and the voltage increases. In order to take a real clear look at data, we developed an algorithm in order to simplify the process of evaluating these curves. So, as talked about earlier, we have the resistance versus the hours, and this is a standard passing versus failing fluid. The same fluid with the algorithm where we've done some conditioning, and then the variability assessed particular conditioning that we did does a very good job. You can see here the passing fluid and this failing fluid, and we have noticed that failures tend to be above 1. So the rating will be between 1 and 5, wherever during the test the maximum value would be. So it's a simple analysis. And as mentioned earlier, the fluids that are field failing have typically failed by the time 600 hours comes around. Another interesting piece which is just additional data, are the traces that run on the outside of the board, both in the oil and vapor phase. Here, one can see that the failing fluids tend to have a steady rise, where the passing fluids tend to be straight across. Here are some fluids that were borderline fluids, where you can see a steady state. So again, an algorithm is being analyzed to see if we can differentiate between these fluids. Let's look at the precision, a little bit of statistical analysis. Fluids that fail in the liquid only fail 100% of the time. Fluids that fail in both the liquid and vapor 88% of the time. For vapor phase only, there's not enough data for statistics here. There's only one fluid that was doing that. But for passing fluids, 92% of the time. And the few times it did fail, we felt that they were aberrations of the test, which have been rectified since that time in the electronics. Typically, we like to see 2 replicates, and the data you're seeing, these were run 3 times every time. So this test does appear to be a good discriminator between good and failing oils, both with off-the-shelf fluids and with those that we know fail in the industry. Well, let's move on to the next test. Let's talk about the wire corrosion test, also known as the WCT. The concept of the WCT is to evaluate the chemical reactions forming corrosion. That is done at temperature and watching the reaction rate in real time. So the rate of that is being evaluated through a resistance measurement, similar to the CDT. But here, the demonstration where one can see the corrosion buildup on the wire and the depletion process rate over time. Let's take a look at the WCT testing parameters. Various fluids may be run within this fluid, typically ATF or AGO. Temperatures between 80 to 150 degrees C are standard. A lot of the test results that you'll see here are either at 130 or 150 degrees C. Oil volume, approximately 400 milliliters. Test time, 70 hours. So a relatively short test. And again, evaluation of both the fluid phase and the vapor phase for the wire. So the wire comes down here and then is cross-linked between these fingers on the holder. That is placed into a liquid bath and then powered in a 5-volt DC circuit and data logged over time and monitored. So what's interesting here is that we're actually going to monitor the outside diameter of the wire. But first, let's talk about what's happening. So the molecules of copper are allowing conductivity of electrons coming through here from positive to negative voltage. The copper loss due to corrosion increases the rate of resistance. And during that time, the actual wire outside diameter is physically affected. So the loss of copper as molecules come off, the higher the resistance. To be crystal clear, let's take a look at some photos and some actual results on the wire corrosion test. This is your copper loss in angstroms in your time in hours. And as you can see, the copper loss increases depending on the amount of corrosion. There's a lot of corrosion going here, so it's very rapid. And then here you have a little bit of corrosion, as you can see here, depicted in this graph. And then taking a look at something with the medium amount of corrosion somewhere in between. So let's take a look at what we'll be analyzing. So what came out of analyzing the amount of corrosion, we're actually able to utilize an algorithm to take a look at the projected amount of radius loss or diameter loss on the actual wire itself, and the correlation of this between actually measuring it by removing it and analyzing it, say in an SEM, was accurate. So the algorithm utilized here is quite good. So here's copper and AGO and copper and ATF, and looking at the differences of the radius change over time and hours and how those were affected. Of course, you have the failure rates. Like you saw, this relates to the previous graph, but this is actually looking at the change and the different fluids here. So as you can see, it's quite consistent and accurate and tells the user a lot about the various fluids. So let's take a quick look at the repeatability of the WCT. Here are several laboratories with repeat runs at the same temperature. And as you can see, looking at the radius change versus the time in hours, repeated very well. Lab 1 had 1 repeat, Lab 2 had several repeats. This has now been sent out to multiple laboratories, and the conditions are the same, where the repeatability looks very good. Now that we have covered the WCT and the CDT, let's give you a quick current industry update. For both tests, SAE J3200 proposal includes both of these tests. The instruments have been taken into consideration at ASTM within Subcommittee 9. And for Subcommittee 9, the first test, the CDT, has already had quite a few participants, and an ILS will be beginning. The WCT will be right behind that one. The test methods are written for both tests. As mentioned, the ILS will follow as a protocol. And the tests are written as a U.S. Army Mil Spec or FTM, and those are being approved at this time. Other proposals are currently in process for specifications around the world. A quick thanks to Ford Motor Company, APL, and Lubrizol for Arup, Gunther, Rico, and Tim. Appreciate all the time that they put into developing these tests and working with the group. And I would also like to thank Greg Hunt as the co-author of this paper for all his hard work in these areas. Thank you for your time and attention. More to come. Stay tuned. Bye for now.